Okay, part two, we're supposed to figure out the magnetic field strength inside of the wire at a given radius. So again, the hard part of this problem is figuring out exactly what the equation is that we need to write. So, um, so let's think about it here. We have a current traveling along the wire, which means that there's a magnetic field generated um, that would be tangent to the radius of the curve. So here's a little chunk inside of the wire, a little slice of a cylinder. And inside of that, at that point inside of the wire, there's a magnetic field that is that's tangent to that circle. Um, we know that we can figure out what the current is because we now have the equation that we derived from the first part of the problem. So we're kind of led by the nose to use Ampere's law, which says that the closed line integral of B dot ds is equal to mu naught times the current enclosed. We know that B dot ds, which is B times the um, cosine of the line integral, is going to be the angle between them will always be 0, and so we'll get a cosine of 0, which equals 1. And so that this just becomes B times ds. But ds is really just the sum of all the little slices all the way around the circle. So that's 2 pi r. And then we have mu naught, and we know that we can figure out what I enclosed is, right? Remember that I enclosed is going to be uh, J equals I over A, which is also equal to 3I, 2 pi r squared times r over r, oops, little r, over big R. And so I take this and multiply it by A, and I'll get the current. And so then this is mu sub naught, and remember that this is the current density at a single little tiny slice of a radius, dr. So we need to sum all the way up from 0 to little r, all the little slices of the current in order to figure out what the current is inside of that little chunk. So this is the integral from 0 to little r, from 0 to little r, of 3I over 2 pi r squared times r over r, oops, r squared over r, times the area enclosed in there, which is 2 pi r. Okay, I'm going to move over here a little bit. We have a ton of constants, so let's pull them out, and then the um, integral is going to be trivial to solve. So we get mu naught 3I and 2 pi over 2 pi and r cubed. And that's it. So now we get the integral from 0 to r of r squared, that was what was left, r squared dr. And that's easy to solve, right? That's r to the third over 3. And so I'm going to get mu sub naught r to the third over 3 is going to cancel that 3. So this is going to become mu sub naught over, or times I, times 2 pi, times, pull the r to the third out there, times 2 pi over r to the third, big R to the third, evaluated from r to 0, and that'll just stay the way it is. So what we end up with is this equation, and I'm leaving the 2 pi's in there because I can't quite remember exactly how this is going to work, but I want to get mu sub naught over 4 pi. So we get b times 2 pi r is equal to this. Mu sub naught times I times 2 pi r to the third over 2 pi big R to the third. And now I'm going to divide both sides by 2 pi r. And so these 2 pi's will cancel. However, remember I want this 2 pi to be a 4 pi, so I'm actually going to multiply the whole thing by 2 pi over 2 pi. And what I'll get is b is equal to mu sub naught over 4 pi times I 2 pi r to the third over big R cubed. And that should be my answer. Can't remember if that's what's in the back of the book, but that is indeed what the answer should be. Mu sub naught IR squared. So I must have lost an R somewhere. R squared. Oh, I forgot to bring over a 2 pi R. So there's an R here that cancels with one of those. And so this becomes R squared. So that's how the problem gets solved. And if we let little r go to big R, then we will indeed get mu sub naught over 4 pi times I times 2 pi r over r squared, which is the field strength inside of or outside of a long current carrying wire. So that's how you solve the last part of the equation.